Welcome everybody to our June meetup. Yeah, I've been so excited for this one. This week, or this month, sorry. We have Dave Farley with us, he's going to be speaking to us about scaling up our software development. Been so looking forward to it. I mean, he's got nearly 10,000 followers on Twitter, I think you do, and an author and founder of Continuous Delivery. So yeah, we're very excited to have him here. But I guess a little bit of housekeeping before we kick off. If I can change it to slide. So firstly, who are we? So my name's Chris, for those of you who don't know me. I'm kind of one of the organizers of AnyTech. We also have James, Mark, and Martha. Unfortunately, they couldn't be with us this evening. But I guess collectively we kind of make up the AnyTech team and arrange meetups and all the good stuff around that. If you did want to get in touch with us, then there's our social media handles. Feel free if you had any questions or feedback for any of us or for Dave, and we can pass that on. Similarly, if you wanted to speak at AnyTech or you knew anybody who wanted to speak at AnyTech, then do just get in touch. We're also kind of all over the general social media, all of the common ones, as well as a Discord channel. Easiest way though, if you just go to any.technology and there's a contact us page there, and you can find all of those links on that page there. As well, you'll find kind of the upcoming meetups and all of our previous meetups on there. Yeah, you can get all the information on there. Big thanks to our sponsor, Scott Logic. Usually when we do physical meetups, we kind of have beer and pizza for everybody. But for the obvious, we're doing virtual meetups. Yeah, I guess without those guys, we kind of wouldn't have a meetup. So big thanks to them. So without further ado, then I will kind of hand this over to Dave. So yeah, he's going to be speaking to us about kind of scaling up our software. If you want to get in touch with them, then there's his kind of social media handle on Twitter, and he's also on YouTube as well. He's got some great videos on there. In terms of questions, feel free to chuck them in the chat, but we'll arrive to those at the end of the talk. Cool. All the stuff to say, and yeah, Dave, if you want to take the screen, then the stage is yours.
Great, thank you, Chris. Okay, so hopefully you can see my presentation on the screen. Let me just make that full screen. There you go. Right. So my topic is scaling up, but it's kind of intentionally slightly misleading. I probably mean scaling up in some different ways and different dimensions. So certainly about bigger, going bigger, more complicated software, all that kind of stuff, but also kind of scaling up in terms of how do we just do this better is another way of thinking about it, I suppose. And that's really my theme for this evening. So let's start. So I think that when we often think about building more complex systems or stuff like that, we start to get pictures like this into our mind, and thinking about, what goes on in the real world. And that's kind of interesting. The stuff we can kind of think about and learn from that to some degree. But there's a big problem is that this isn't our problem or even close to it. Our problem is distinctly different. Software is unusual in one particular respect. It's unusual in a few different respects, but certainly in this one, in that software, unlike anything else that's gone before it, really, doesn't have any production costs. So for us, the output, our product, is a sequence of bytes. So however complex the system that we create, we can capture that as a sequence of bytes, and we can clone that sequence of bytes for essentially zero cost. That's weird. That's unusual compared to most things that we as human beings do or have experience of doing. And it has some implications, because we often think about kind of taking ideas from other disciplines. I think waterfall was one of those. It was kind of like a production line for software development, but it's not applicable. It's not the right kind of model, because we don't have a production problem. So we don't need production lines because we don't have a production problem. Our problem is always down, is hugely influenced by this idea that we can recreate entire systems essentially for free for as many times as we like. So that's not our scaling problem. Our scaling problem is very different, and this has big implications. One of the things is it means that throwing people at the problem doesn't work at all. But that's the common kind of reaction to trying to scale up in terms of going faster or building more bigger and more complex systems. So ours is not a production scaling problem. And this means that applying ideas like production line thinking is completely wrong. This is not about trying to find cookie cutter solutions, because if there's a cookie cutter solution, we can recreate the solution as a sequence of bytes for free. So reproducible standardized approaches don't make an awful lot of sense either, because that's never the game that we're in, because if it was reproducible or standardized, we could do it for free. So software development is always, every single time, an exercise in learning and discovery. That doesn't necessarily mean that each of us is kind of finding new knowledge for humanity every time that we do anything, but within the context of ourselves or our team, it's always an exercise in learning and discovery, because otherwise we just use what we had before. So that means that we should be optimizing for learning. It should be a professional duty of ours to become world-class at learning. If we want to become world-class at learning, there's a good model for that, and that's kind of science. So we can think of, how does science learn, and we can apply some of that kind of thinking informally to what it is that we do. One of the first ideas that seems central to our ability to learn is working iteratively. This seems pretty obvious these days, but it wasn't always obvious. There's still an awful lot of organizations, despite people dismissing waterfall and everybody knows it doesn't work, there's still, most big organizations still work or are still informed by waterfall style thinking. Iteration is much closer to the kind of thing that we want, though. What iteration gives us is the opportunity to try stuff out and figure out what works and what doesn't. That means that we need to collect feedback. We need to gather information about what it is that we're doing so that we can learn from that. So we can make database decisions rather than just crossing our fingers and guessing at things. We'd like to be able to collect data and understand, what it is that we're doing. We'd like to work incrementally so we can start to divide up the problem. We'd like to work on parts of the problem separate from others. And that's one take on what incremental thinking means. If we're going to start working in this kind of way, iteration-based, feedback-based, making incremental steps, it means that we need to become experimental. We need to be trying ideas out and figuring out what works and discarding the bad ideas and running with the good ideas. And also, if we're doing engineering rather than pure science, we need to be empirical. We need to be trying things out in the world. We need to understand what really works. One of the things that I'm fairly obsessed with at the moment is tracking what SpaceX are doing, building their Starship rockets that are meant to take people to Mars. They are busy doing world-class engineering at the forefront of learning by blowing up spaceships in Texas on the journey of building lots of prototype after prototype to figure out what works. That's empirical learning, visible on YouTube, you know, as they go. Software development is also about managing complexity as well as being about learning. We build systems that are bigger than we can hold in our heads in one go, and we build systems on, you know, in organizations that are bigger than we can understand everything about what's going on sometimes. So that means that we need to also be able to manage the complexity of the problems that we're dealing with, so we can kind of effectively compartmentalize the things that we're working on. That brings in ideas like modularity, abstraction, separation of concerns, loose coupling, cohesion. These are the tools that allow us to deal with the complexity of the systems that we're working on. We'd like to be able to make a change in one part of our code without screwing up every other part of our code. We'd like to be able to make a change in one team and not force change on other teams as a result. We'd like to be able to, you know, decide that we'd like to store our stuff in a different kind of database to the one that we were storing it in before, and that not be crippling to the design of our software maybe. But all of these ideas allow us to start to think about compartmentalizing the complexity and dealing with it. One of the interesting things, I think, one of the things I didn't really understand until a few years ago, but information's kind of a slippery idea, and when you think about it, you know, in terms of information in its pure sense, then information is just as true of the organizations that we work in as it is of the software. And yes, this is kind of related to kind of Conway's law, but I think there's even more to it than that. Conway's law stated that we're kind of doomed to replicate the communication structures in our organization in the software that we build. But even more than that, ideas like coupling and concurrency matter in the way that people work as well as the way that software works. So we need to think about those if we are to do this at any kind of scale, at any kind of pace. So what do we need to do? I think there's a few starting points. One of them, I think, is to recognize that software development is a creative discipline. In engineering, you know, it's an engineering design discipline. It's about being creative, genuinely, in the sense of coming up with new information, and that's really what I mean when I talk about learning. Dependencies in the code and in the organization are one of the key stumbling blocks to us doing this for anything but simple, trivial, small pieces of software. If we aspire to being able to create things that go beyond that kind of scope, then we have to understand and start to take these problems seriously, because they are fundamental. There's no avoiding them. We can kind of sometimes duck them a little bit for a while, but if they come back to bite you, they bite you quite nastily. So we need to start thinking about applying this kind of creative engineering thinking to software, I think. Here's a few principles that I've come to value and to think are important. I've mentioned the first two already. We need to start to optimize for learning, and I mean that consciously. We need to start approaching everything that we do in that what we are, our primary goal is to learn, and secondarily, that's how we get good delivery. If we focus first on good delivery or fast feature delivery or something like that, we get poorer outcomes than if we focus most on learning, because that's how we get to solving the problems simply with less work. Managing the complexity allows us to scale in a variety of different ways. The next on the list is kind of controlling the variables. If we want to start thinking a bit more like engineers, it means that we want to be able to I don't know, get the same results every time we deploy the software. Every time we run a test, we'd like it to get the same results every time. If you've got flaky tests or race conditions in your code, the variables aren't sufficiently controlled. If you are running soak tests for long periods of time, you're not measuring precisely enough. The variables are not sufficiently controlled. So there's more that we could do if we want to start applying this kind of thinking. We'd like to make more evidence-based decisions, and so working experimentally, as I mentioned before. So gathering that feedback, understanding what it means, making decisions based on the evidence that we gather, rather than, as I said before, guesswork or hunch. The other thing that I think is pretty fundamental at the roots of what science really is that you start off assuming that any answers that you have are wrong. You don't start off assuming that you've got the right answer. You don't start off thinking, oh, I understand this problem. I know how to solve this problem. You start thinking, well, I'm probably wrong. It's probably going to be more difficult than I think. It's probably going to screw. There's going to be change coming in that I haven't foreseen. All of those sorts of things. And that allows you to start working differently. And that's one of the real strengths of science, is that you kind of learn more when your experiment fails. So trying out experiments, using falsifiability to try out your ideas, is one of the techniques that we can lift from science and start applying in more informal ways to software development. I think there are a couple of tools that I've come to value very strongly. And this for me is one of the reasons why I think that continuous delivery is as popular as it is, and to my mind, as valuable as it is. And those tools are testability and deployability. So let's talk a little bit more about those. First, testability. Let's start by thinking about what it is that we value in good code. What makes good code good? And I've got a list of a few things, and I don't think you might add some more, but I don't think you'll disagree with any of my things. So first of all, it obviously has to work. It has to do something useful that we'd like it to do. Otherwise, it's not really good code unless it works. It needs to be modular. It needs to be loosely coupled. It needs to be highly cohesive. It needs to have good separation of concerns, and it needs to exhibit information ID. I know these are things that I've already said. These are the things that allow us to manage the complexity in our code. But think for a moment about two bits of code. One of them is modular, loosely coupled, highly cohesive, so you can sort of navigate it, you can change it in one place and not affect another. Good separation of concerns, so that you've kind of pulled out, the responsibilities into different parts of the code. So each piece of code that you look at is doing one job. It exhibits information hiding. There's layers of abstraction, so it's navigable. You can kind of find your way around the code because it's got these sorts of landmarks in the code base that kind of tell you where to look for different behaviors. Now think of another bit of code that doesn't have any of these properties or misses any one of them. That second piece of code, whatever the technology, whatever job it is that it's doing, it's going to be worse to work on than code that is modular, loosely coupled, cohesive, with a good separation of concerns and exhibiting information hiding. So these are my 5 things. So let's just look at those in a little bit more detail. So what modularity? So modularity is code which is separated into independent modules. That's fairly obvious. And the idea is that the internal details of the modules are hidden from one another. This decomposes the problem into simpler chunks. It means that solutions are more independent of one another. Solutions are more composable. We can use these modules in different systems or different contexts. And solutions tend to be more scalable, because often it means that we can, if we have more load than we're anticipating, we could run multiple versions of the same module and share the load out between those different modules. It gives us those sorts of properties. It's loosely coupled. So it's one part can change without forcing change on another. This reduces the risk of changing in one place affecting another, helps to isolate problem and so aids modularity, and helps decompose big problems into pieces that we can work on more independently of one another. Cohesion is kind of the counterweight to modularity. My favorite description of good design comes from Kent Beck. And Kent Beck says that good design is where you move all of the stuff that's related closer together and all of the stuff that's unrelated further apart. And that's kind of a joke, but it's kind of true as well. So modularity is about kind of isolating the bits that are unrelated. Cohesion is making sure the bits that are closely related are close together. So this allows us to kind of focus on reducing the complexity of a module. So within a module, all the stuff that's in there is related it's in some way. It improves the maintainability of the code because all of the stuff that we need to change is in one place, and we can see that easily. And it increases reuse because once we've got it cohesive, we can move it about, we can change it and share the changes around. Separation of concerns. Separation of concerns is an old idea. Funnily enough, I was just reading about it today. It was first mentioned, I think, in 1974. But separation of concerns is a design principle that each part of a computer program is focused on doing one thing and doing that thing well. I think this is probably the most fundamental of the kind of design tricks that I use myself in the software that I create. And I worked with a world-class developer, and he had a laser beam focus on separation of concerns, and that strengthened my own view. And these days I use it as a tool. Whenever I'm looking at a piece of code and I think, oh, this does that and that, I'm immediately then trying to figure out how I pull them apart so I don't have to say and when I'm describing any piece of code. It simplifies development. It gives us this focus again so that each piece of code that we're looking at is doing something useful, doing one thing. It's helping to reduce the coupling because that piece is going to be cohesive and focused on solving that one part of the problem. And it simplifies maintenance, testing, and improving the composability. It's a really good guide when you're exploring the possibilities of a design. Using separation of concerns is a fantastic tool to allow you to come up with better and better designs. And then there's information hiding. I tend to talk about abstraction and information hiding in the same breath. There are subtle differences in the meaning between the two, but in this sense, what I really mean is that we want to be able to have lines in the design of our code where there's you know if you're one side of the line, you don't need to care about all of the detail of what's happening on the other side of the line. We need to draw these seams in the design of our code. This reduces the coupling, improves the cohesion, helps with modularity and separation of concerns, and these things end up as being kind of points of stability in the design. What we're aiming for is places in the code that change at a slower rate than other parts of the code, that the implementation detail behind these lines of abstraction. So what allows us to put that kind of quality into the code that we write? Well, I think in the absence of test-driven development, there's only these things: the skill, experience, and integrity of an individual programmer. That's it. There's nothing else really. It's do I know what I'm doing enough to be able to design code with these sorts of properties? Can I be bothered enough to do it? And that's really it. That's all that there is to it. So if you're very good, you might be able to write software that has these properties, but that's kind of it. I want to talk a little bit. Remember, we're talking about testability. So I want to talk a little bit about test-driven development. I think test-driven development is one of the more important things that's happened during the course of my career, and I don't think it's widely adopted enough. And Test-driven development is something very specific. It's about writing the test before you write the code. If you don't write the test first, it's not test-driven development, it's something else. But test-driven development is about writing the code first, and it's best captured by this little mnemonic, sort of red, green refactor. So red is I'm going to write a test before I've got any code, and I'm going to see it, I'm going to run the test, and I'm going to see it fail. I'm going to write just enough code to fulfill the interface demands of the test kind of thing. So at this point, I'm using the test as a way of designing the interface to my code, if you like, the public view of my code. Next, I'm going to write just enough code to make the test pass. We're currently in an unstable position because the test is currently failing. So I'm going to just write the simplest possible step, take the simplest possible steps that I can to make the code pass, the test pass. So I'm just going to do those, even if they're dumb, even if it means hard coding a return value or something like that. And then at the end, I'm going to refactor the code and, if necessary, the test to make them beautiful, elegant, general, while I'm in a stable position of having a passing test. So let's think a moment about what it means to work that way. You'd have to be a weird, strange kind of person to make your own life more difficult by making the test hard to write. So it's inevitable that if you're writing the test first, you're going to try and do something to try and make your life easy by making the test easy to write. And that means that you're going to start falling into a series of kind of reasonably well-known patterns for design to be able to do that. You've got to have certain points that you can touch in the code that allow you to test little pieces of code separately from other pieces of code. So you start introducing ideas like dependency injection. You're going to not like sharing information too much between different things. So you're going to start designing by contract a little bit more. All in all, testable code ends up having some key properties that make it testable. So what makes code testable? Well, obviously it has to work. The test passes and demonstrate that the code works. It's modular. You can see where I'm going with this, right? It's loosely coupled. It's highly cohesive. It's good separation of concerns, and it exhibits information hiding. So test-driven development encourages us to put the properties into our code that we value as properties of high quality code. So in the past, we depended on the skill and experience of an individual programmer. It still does. Test-driven development is not some kind of magic that's going to turn a bad programmer into the world's greatest programmer. But what test-driven development does is it adds to that skill and experience, whatever level it is, and it encourages us to do a better job and get more of these good things. So we kind of get this virtuous circle, this amplification effect, where the skill and experience of the developer, however good they are or bad they are, is amplified by the practice of writing test-driven development. I genuinely think this is one of the few examples that I can think of in our industry of a talent amplifier, that if you just do this, it will almost force you to do a better job. It won't make a bad programmer great, but it will make a bad programmer better, and it will make a great programmer greater. I have a friend who I think he's certainly the best software developer that I've ever worked with. He's world famous. He's an expert in Java, high performance Java programming and concurrency, and I've known him for a very long time. And he's always been a great programmer. But I taught him to do test-driven development, and both he and I think that he's a better programmer now as a result of that. So however good you are, I think this makes you better. However bad you are, it makes you a bit better too. And as I say, there's not much that I can think of that does that. Let me give you a more concrete example. Rather than me just kind of giving you theory, I've got a really, really simple bit of code, and I just want to demonstrate that some of those ideas with this piece of code. So here's a simple class. This is a car, and this car's got a petrol engine, and we've got a start method. So when we start the car, we're going to put the car into neutral first, apply the brakes, and then start the engine. So let's think about writing a test for this. So here's my test: should start car engine. We're going to create a car. We're going to start the car, and that's all we can do. We can't assert anything because we don't have access to the engine. We could do something horrible like make the engine accessible so that we can get at it from outside the car, breaking the encapsulation, but that's pretty ugly. So let's not do that. Let's instead thinking about making this testable. Remember, we do this by writing the test first. I'm not doing that as in this example, but that's the way that we do it. So here's a better car. Again, it's got an engine, but I've changed this in one crucial way, which is this bit. So instead of creating the engine as part of creating a car, I'm now passing the engine in as a dependency injection. That's all I'm doing here. So let's see how that affects the testability of our car. Remember, we would have done this in order to make our car testable. So now we should start a better car engine. So we've got a fake engine now. So what's our fake engine look like? Here's our fake engine. I've just made this up. So we're going to implement an engine interface of some kind. We've got a start method. All this is doing is that it's just recording the fact that start was called, and then it's got a way of me questioning whether start was actually called. In reality, if I was doing this for real, I'd probably use a mocking library to generate this thing for me rather than write it myself, but I just wanted to demonstrate it and not get into mocking and all that stuff. So here's my better car, and I'm passing in the fake engine. Now I'm going to say start on the car, and I'm going to assert that the engine was started. There's my test. So let's just think about what that means in terms of the design of my code. I would argue that this is better in most of the ways that I mentioned before. It's more modular because we've separated out the car. It's more cohesive because the car bit is now separate from the engine bit, and we're not really confusing the two. It's more loosely coupled because I'm passing in a different engine, or I could. In the test. If I was in reality, if I wanted to use my better car, I can certainly create a better car with a petrol engine as I could before, but I could also create a better car with an electric engine without changing anything about my car. This is still valid. My test is still going to pass, but in production, I could use it with an electric engine. And if I was some kind of crazy person, I could create a better car with a jet engine if I wanted to. This has made my code more flexible. It's more composable in different ways. It's easier to test. It's easier it's more valuable as a piece of code. The next in my tool chest is the idea of deployability. We talked about testability and how that can be used as a tool to help us drive these aspects of quality into our design. Deployability is a slightly different thing, but an interesting one. This is a picture that I use to represent the idea of a deployment pipeline in continuous delivery. A deployment pipeline is a more specific thing than I think most people give it credit for. I think often when people think about deployment pipelines, what they really mean is a build script. Maybe a build script that's hosted by Jenkins or something like that. That's not what I meant. So I'm the person that came up with the term deployment pipeline. That's not what I meant when I came up with it. A deployment pipeline for me goes from commit to releasable outcome. we're going to generate something releasable. Oops, sorry. We're going to generate something releasable. Every time we commit something, we're going to, damn, I pressed it again. Every time we commit something, we're going to evaluate it to the point where it could be deployed into production without any more work. That means that everything that constitutes releasability for our software, deployability for our software, is in the scope of the evaluation of our pipeline. Imagine for a minute what that would mean if you've got a deployment pipeline like this and you've optimized it so it's going to give you an answer, let's say, at least once an hour. So every hour, you know whether your change is good to go into production. Once an hour, you've got a releasable outcome. Think about the impact that that would have on your work, your ability to make a change, try out an idea, see if it works out okay, and if it doesn't, back it out. Make a change to do almost anything and just try it out, see if it's ready to go into production. And if it doesn't, back it out. I can give you a concrete example of doing that. I was involved in building a very high performance financial exchange using these kinds of techniques. We'd once decided that we didn't like the commercial terms that we had with our relational database vendor. So for a data warehouse, one component of our system. So we went and downloaded MySQL. We scripted the automated deployment of MySQL in the context of our application, and put it into the version control system and tied it to one of our release candidates and put it through the deployment pipeline. And we ran the tests. Two of the tests failed. So we looked into what had failed. We fixed the problems, committed the changes, and it went through the deployment pipeline again. At the end of that, what we had was something that had passed all of our testing and was ready to go into production. The following weekend, when we went into production with a version with the new database. Now, the whole story that I just told you took one morning on this project. Because we got this experimental platform, we got all of the tests, all of the evaluation, our software was deployable, and using the deployment pipeline to assert the deployability, the releasability of our changes, allowed us the freedom to try out, to experiment with this change and see whether it worked out. If it hadn't worked out, we would have burnt a morning. That was all. We probably would have taken the rest of the day to see how far it got, depending on how it failed. But that kind of thing, I've worked places where that wouldn't be possible, and I've worked places where just that would have been an exercise, you know, for a small team for a few months to try and fix that kind of problem. So using deployability gives us a different kind of insight into the releasability of our code. One of my definitions for continuous delivery is working so our software is always releasable. So deployment pipeline and the idea of deployability is fundamental to that. So what does deployable mean? It means that there's no more testing to be done at the end of the deployment pipeline, because the deployment pipeline did all of the testing. All of the testing that we need to do prior to release is within the scope of the deployment pipeline. There's no sign-offs to do anything. If there's any sign-offs, that's part of the deployment pipeline too, because that's part of the releasability, the deployability of a change. There's no integration test with other components of the system, because the scope of the deployment pipeline is a releasable unit of software. And that's what we're trying to get to. That's what deployable really means in this context. So if we're interested in doing a better job, scaling up the quality of our code and the size and complexity of the systems that we build, then we've got to take these ideas seriously. These are the tools of our trade. I think these are the tools of the trade, whatever the nature of the software that we build, for whatever purpose, with whatever technology. These are the principal tools that allow us to scale software development, whatever we mean by that, really. So what do we mean by scaling? There's a bunch of different angles to this. We can think of, can we scale the size and complexity of the systems that we create? Can we scale the quality of the systems that we create? Can we scale the size of the organizations to create things more quickly? The last one's done. The last one's what everybody tries to do, and that doesn't really work in the way that most people try to do it. There's a beautiful, famous quote, again from the 1970s. I'm having a riff on the 1970s tonight. So Fred Brooks, who wrote the fantastic and still perfectly accurate book, The Mythical Man Month, in the 1970s, said in that book, you can't make a baby in a month with 9 women. There's a certain level of parallelization inherent to a problem beyond which you can't go. You can average a baby a month with 9 women and 9 babies, but you can't make 1 baby in a month with 9 women. So adding more people to a problem doesn't necessarily allow you to go faster in solving that problem. There's some lovely research that backs that up. We've learned over the years, this used to be more revelatory, I think, than it is in the old days. But these days, we kind of learned, you know, we've learned a bit better. And there's research, there's data that looks into the behavior of small teams versus larger teams. There's this nice metadata study, which I particularly like. In a study of over 4,000 completed projects, including complex projects of all different kinds, they divided the cohorts into 2 groups. They looked at teams with 5 people and fewer, and teams of 20 people and more. And then they did some fairly simplistic data collection to try and figure out the difference between these 2 teams. The first thing that they looked at, you can argue all you like about the value of it, but it's easy data to collect. How long did it take them to get to 100,000 lines of code? Well, on average, it took the 20-person teams a shorter time than the 5-person teams, as you might expect. But on average, across everybody, it took about 9 months to complete 100,000 lines of code from scratch. It took the 20-person teams on average 1 week less time over a period of 9 months than the 5-person teams, which means that a 20-person team is nearly 4 times less efficient than a 5-person team per head. And then you look at the defects. The teams of 20 people or more created 5 times as many defects as the teams of 5 people or fewer. So small teams are the only way to go. Large teams make no sense whatsoever. So if you're thinking about scaling up in terms of growing an organization, you want to be able to have many small teams, not few large ones. And then there's this picture, which I loved when I found. This is based on something called nonlinear dynamics and complex adaptive systems, as studied by the Santa Fe Institute. They look at the sort of complex nonlinear dynamics maths, and one of the things that they looked at was things called space-filling networks. So mathematical structures, rather like this, that represent ideas in the real world in complex adaptive systems. On the screen at the moment is a typical kind of representation of a big organizational structure. You've got a hierarchical structures. At the top, there's a CEO or a CTO or something, and then lower down, you've got ranks of managers and groups of people organized below them, with different sorts of lines of reporting represented. When you see this pattern, this kind of structure in information systems, whatever the nature of the information system, there's this number that keeps cropping up, 0.85 or 85%. If you have an organization, for example, that's structured like this, and you double that organization in size, then the productivity or profitability of that organization only goes up by 85%. You don't get a one-for-one scaling. So there's a law of diminishing returns. The bigger the organization grows, the less the gains. But there's a flip side to this. If you have an organization like this and you need a certain amount of infrastructure, then if you double the size of the organization, you only need to add 85% of the infrastructure. So there's some cost benefits as well on the flip side. If you have a city that's organized like this, the maintenance and organization of that is structured like this, and you double it in size, you only need to add 85% more petrol stations, for example. This is weird maths. It's just kind of unavoidable, it seems. There's another kind of space-filling network, and that's this. This is the small local distributed network kind of model, kind of social media, sort of little clusters, little groups loosely affiliated with other groups. It's not hierarchical in the same way. This too has its number associated, and the number associated this is 1.15. An organization that's structured like this, and there's a famous one, this is how Amazon is structured. An organization that's structured like this, if they double in size, they more than double in productivity, in revenue, whatever measures you want to do. So Amazon, every time it doubles in size, its profitability, productivity more than doubles, which is kind of scary in some ways. The costs increase in the same proportion. They go up by 115% as well. So it costs them more to kind of support all of these independent teams. But the maths says that you can't avoid this. This is pretty fundamental. This has some deep implications for scaling an organization. And you can kind of organize yourselves in different ways. But one of the trade-offs that an organization like Amazon makes by taking this strategy is giving up consistency. There's no central control here. Each of these teams is responsible for itself. It's the most scalable way of working. If you genuinely want to scale up, that's how you do it. You make each of the teams essentially independent of all the others, and with very loose relationships between them. The picture on the left-hand side is the much more traditional picture, the one that we're mostly more familiar with in most organizations. And for those kinds of things, they can have consistency, but you get this law of diminishing returns. There are limits to how big it can grow. It can't go beyond a certain limit, which is probably why Amazon and Google and organizations that have adopted this kind of model are kind of owning it in cloud territories and those sorts of places. This has implications because the kind of models that you use to design the software change depending on those kind of approaches. The only way to do the picture on the right, the Amazon model, is with microservices, independently deployable units of software that each team owns, and you don't get to test them together before you release them. It's the only way you can do it at that kind of scale. So to scale up problem solving, you need to distribute problem solving. That's how you do it. What does leadership mean in an organization like that? You've got an autonomous team that makes its own decisions, does its own things, decides on its own direction, makes its own technical choices, working with deployment pipelines, optimizing its feedback loops, all of those kinds of things. So what does autonomy mean organizationally? How do you do that? Well, there's still a need for leadership to some degree, otherwise it's not really an organization. And the role of leadership is really different. The objective of leadership in these sorts of organizations is to define the strategic intent. It's kind of I always imagine it, leader's job is to plant a flag on a hill and say, wouldn't it be brilliant if we got to there? No idea how to do that. You're smart, figure it out. It's kind of this mission-based planning. And then sort of boundary parameters. You know, here's what you need here's enough money for you to go and experiment and figure out how to solve this problem. There might be some commonalities that you want to put in place to save every team having to reinvent the wheel from scratch. But these need to be pretty generic, pretty common, pretty widespread. Take a look at AWS. That's why AWS exists, because it was built to support these autonomous teams within Amazon. So things like S3, which are block storage on AWS, they're deeply decoupled from the teams. The S3 teams knows nothing at all about the teams that are consuming it, even the teams inside of Amazon. They just provide an interface and they allow people to use the tools. So common tools and tactics. When Jeff Bezos made the move within Amazon into this model, part of the communication that he sent out to everybody was, you know, you're each going to be working in small teams, no bigger than can be fed by 2 pizzas, and whatever you build, you're responsible for. It's up to you what you do, how you do it, but it can only communicate with anything else via messaging. That was it. So those are kind of the tactics, the common tools, and then there's the strategic intent, you know, in terms of business, general business direction, the vision for the organization, I suppose. So what are some of the techniques that you can use to breed this kind of autonomy? One of the things that I like is this for teams. What you need is that you want to get some kind of consensus about the big picture things. And this is sort of fractal. This works at the level within a team, but also at this sort of strategic intent thing. So if I'm working as part of a team, you know, my ideal for a team is that everybody on the team, if somebody came to any member of the team and said, we've got an idea for a new feature, all of us would share a common view about where we'd want to put that feature. We'd all have a similar kind of model for where we're likely to want to put things. So we've got this kind of high level picture of what it is that we're talking about. Yes, I'm kind of talking in general terms about architecture. The ideal kind of architecture, to my mind, is accurate but vague. We want it to be vague enough that we can kind of change our mind in useful and sometimes subtle ways, but accurate enough that we can have sensible conversations. This picture here is a real one of those diagrams. This is a kind of tool for exploring ideas. So, you know, if somebody come and talk to the team about this, that own this, they would say, well, do we put this in the public API or in the web API, in the clearing gateway, the execution service, whatever it might be. And we could have those kinds of conversations. I like to think of these as kind of tourist maps for the workings of the system. Rather like a tourist map, it's not detailed enough for you to be able to precisely locate yourself with some kind of huge geographic accuracy, but it's good enough that you know where you are and how to work from one part of the system to another. It kind of gives you that kind of picture. I think that's a useful sort of mental model for the kind of thing that you want to do. You can use these at quite high levels. This picture on the screen here was pretty much the majority of an enterprise system for a whole business. So one of the tricks. Sorry, did somebody have a question? No, okay. So one of the tricks is to consciously try to avoid too much detail. One of the other uses for this is that this is the tool that you use to introduce new team members. You use this as a tool to kind of tell stories about the system, to explore it. I call these whiteboard models, and the reason that I call them whiteboard models is that one of the techniques to kind of constrain the level of detail that it goes into is that you want any member of the team, at least any senior member of the team, to be able to recreate this on a whiteboard from memory. So it's got to be accurate enough to be able to tell stories about, but lo-fi enough, vague enough, abstract enough that you can remember it, and you can store that as your tourist map of the system. The other tool that I think is enormously valuable to be able to facilitate some of this kind of stuff, and certainly allows us to scale up in terms of our learning, is pair programming. Actually, pretty much pair everything. Human beings work better, they're more creative when they can bounce ideas around other groups of people. It can be more than pairs, but I think at least pairs is a good starting point. I've seen this technique unlock learning in teams so many times that I value it enormously as a tool to help teams to start making changes. Certainly when we start thinking about scaling up and sort of trying to get these sorts of changes into an organization, you know, thinking about what leaders do for those sorts of organizations is useful. And I would suggest that the primary role of leaders is to teach people, not to tell them what to do. You know, my job as a leader of teams was not to tell everybody what to do. My job was to hire people that were smarter than me and say, go on, you're clever, go and solve, you know, sort things out. And that's what I aspire to do. So if we want to scale up, then we need to scale decision making, and we do that by making it pervasive, distributed, and continuous. We want to be making decisions everywhere in the organization, and we want to be making decisions all of the time, not at specific fixed moments. That's the end of my talk. And so I'm going to stop sharing my screen now. A couple of links. I've got a blog site on here, which you can go and have a look at, some of the thoughts on that. You can follow me on Twitter, links to other stuff. And I've got a YouTube channel, which is quite popular, which talks about this sort of stuff and lots of other things. We're rapidly approaching 60,000 subscribers. So if you aren't already, please do subscribe, and there's more stuff on the YouTube channel. So I'll stop sharing my screen. I'm more than happy to take any questions now.
Well, I guess I had a question. So you mentioned about TDD, but I guess like I understand like the benefits of it, but in my experience, I see a lot of teams actively not doing it. What do you think is kind of the main thing that's holding teams back from adopting such a process?
I
know it's very like individual, that, but
yeah, I think that the main thing is resistance to change. I think that the main problem is that's not how people are taught to do programming. I hope that when my granddaughter learns to code in kindergarten, then she learns in the context of test-driven development. That would make sense to me. I think that I have come to the albeit hardline approach, is that coding makes less sense to me in the absence of tests than it does in the presence of tests. So it would be great if that's the way that all of us learned how to do it, but we're not starting from there. So the biggest barrier is that's not how we've done it up to now, and resistance to change. More practically, so sorry to advertise my YouTube channel. I've got this week's video. I publish videos every Wednesday. This week's video is specifically on that topic, and it talks about 3 different problems that people point out. One of them is that the tests are are hard to write. The other one is that over time, the tests become a barrier because if you need to change the code, you have to change the tests. And the last one is that you end up with poorer designs by driving them from test-driven development. And as I said in the video, I'm afraid I think that those are symptoms of bad TDD. They're not inherent to TDD at all. That's people not doing a great job of TDD. So what do you do to do a better job of TDD? Well, the objective of the test in the the example is to assert the behavior of the code that you want to do. So you focus, whatever granularity you're writing the test, even if you're writing a really fine-grained test, then what you're trying to assert is that the code exhibits the behavior that you want. Remember back to the car test that I wrote? I had a test that started an engine and then said, did the engine start? Doesn't say anything about engines work or how the car works or anything else. It didn't say anything about putting the things into gear or anything else. That was within the behavior of the car. I'd probably want some other tests to test some of those things, but the scope of my test. So I could change loads of details about my car and that test would still be correct. So the way that you write the test, focusing the test on the desirable behavior of your code is a good starting point. What that does is it makes the code easier to write. So if I'm starting out and I don't know where to begin and I'm thinking, well, I want to write a car and what do cars? Well, cars have engines, and I want to be able to start the engine. So okay, so I'm going to write a test, and it's going to say that I've got a car, and when I start the car, the engine starts. That's easy to imagine. I haven't thought too much about how I'm going to make that work, so I could write that test easily. So writing that's easier than writing the kind of messy, horrible test that you end up if you write the test after you've written the code. That's simpler if you write it first. And it's more loosely coupled with respect to the code. So now I can change my code. My test stays true as long as that's the behavior that I want. So certainly there will be times where I need to change the test and the code, but they're going to be much, much less frequent if I take that approach than if I take the commonest approach to what people call test-driven development isn't test-driven development at all. It's unit testing, whereas you write the code first and then you try and write some tests afterwards, and you end up with these horrible bloated monstrosities. There's a good example of a horrible bloated monstrosity in this week's video. That's way too tightly coupled to the code underneath. And the last thing is about the design. So I think I've demonstrated the ideas of the design is that by writing the test first, you tend to be pushed in the direction of this more modular code with better separation of concern, all these things that we value in design. So I think if you do the behavioral approach to writing tests, you get much, much, much better outcomes. But people aren't used to it. They're not used to thinking this way, and that's the biggest barrier. I don't get it. I am now of the position where I don't really think people are doing a professional job unless they write tests, and that's where I'm at these days.
Can I offer an opinion? Hi, my name's Andy.
Of course.
So I do quite a lot of recruitment for my company, and I actually do insist on TDD. But what we find is when people come out of universities, they don't know anything about test-driven development. Yeah. They've heard of it, but they have never practiced it. And quite often, companies, in my experience, when you go and work for them, they don't train people in test-driven development. They don't endorse it. So I think that's what the problem is.
Yeah, and I think you touch on a broader issue in the industry, which is an important one. Which is I think so I think universities, on the whole, don't do a great job of preparing people for jobs in professional software development. They teach them the wrong things. They teach them, details of computer science that don't really matter as much as the practicalities of how to build good software systems. And I think that's a problem. So I'm with you. I think that test-driven development should be on day one of your university course, if not in kindergarten. I think you'd be starting from there. The other thing that you mentioned, which I agree with again 100%, is that industry is terrible at teaching people, and it's essential because of the problem with the university training. Everybody learns on the job, so everybody's learning and making the same mistakes that we were making in the 1980s and 1990s. There's very little advancement in that sense, in my view, as a result of that. The tech moves on somewhat, but in terms of thinking and approach to development, moves are really slow, and people are still making the same mistakes that I saw being made in organisations in the 1980s, and that's a problem. When I was in the middle of writing my book Continuous Delivery, I got a job, a kind of dream job, working for a startup. So I was headhunted by a friend of mine to start this company where our goal was to build one of the highest performing financial exchanges in the world, from scratch, blank sheet of paper. And I was hired as the head of software development. So I was responsible for recruiting all of the technologists that came onto the team, all of the developers. And we decided on a specific hiring approach. We were going to hire, so my friend was the CTO, I was the head of software development. Between us, we interviewed every developer that joined our team while we were at the company. So our hiring strategy was we were going to hire people that we knew personally were good, and then we were going to hire young kids straight from university, and we were going to brainwash them into working the way that we thought was good. And I am very proud to say that we helped to start the careers of some very, very talented, very, very good software developers as a result of that practice. I think universities are higher education is letting us down. In industry is letting us down in terms of not spending enough time and effort to train people, to bring people on. And one of the tools that facilitates all of that, in my view, is pair programming. If you join a team and however junior, when somebody joined our team on their first day, they would be, however junior, they'd be working on code that would be in production the following week. They'd be sitting alongside somebody that knew their way around, who'd help them learn and adapt, even if they'd never done test-driven development or pair programming or any of those things before, never worked in finance before. They'd be sitting with somebody who could help teach them. Good points. Thank you, Andy.
I guess I completely agree with that. I remember a while back I did a computer science degree, and I'm a tester now. And I remember being in university and I'd never really heard of testing before. And it wasn't until I actually got my first job that suddenly my eyes were opened a little bit, wow, this is actually the real world, And 90% of my degree I don't use anymore. Which is probably common for a lot of degrees, and not to throw computer science degrees under the bus or anything like that. But I think they're very sort of broad, so they don't home in on the stuff that you would actually use in a kind of software development career.
Yeah, I absolutely believe in learning for learning's sake. I think a university education should be more than just preparing you for a job. But I think that there's a degree to which, that there's a level to which academia has become detached from the reality of professional software development, which is difficult. It means that I can see. I have done this. I have hired people with no degree whatsoever. I have hired people that had a completely different degree. If I'm honest, I couldn't tell any difference between people that did computer science and any other kind of technical degree. If I'm really honest, probably prefer to have a physicist or a chemical engineer than a computer scientist to be a developer, because they've got a bit more scientific style thinking, engineering style thinking on the sorts of teams that I've worked on. Those people, the people from those sorts of backgrounds have some problems of their own. They're coming assuming that software development's easy, and it's not. But I think it's an interesting problem, and I think we could be doing a better job in the universities around some of this stuff. I think there's stuff that we've learned that should be part of the curriculum, and yeah, you want some of the computer science stuff, so information theory ideas, all that kind of stuff as well. But how many computer science degrees have a module that covers experimental practice or the scientific method, for example? How can it be a science if you don't talk about science? You don't learn about science. It seems odd to me. Sorry, I'm ranting. It's the end of the day, and I'm ranting. Sorry.
Cool. Any more questions at all? Feel free to unmute yourself if you did have a question.
No questions, but just wanted to say, enjoy. That was really good. Thank you.
Thank you. Pleasure.
Cool. Okie dokie then. I will just steal the screen then. Just kind of close off for the evening. There we go. So yeah, firstly, just big thanks to Dave. That was just an awesome talk. It's great to kind of discuss the sort of our software development and how we kind of arrange our projects to get the most out of them. If anybody did have any further questions or anything, then there's some social media handles there. I'm sure you can kind of find Dave. Those all over social media, YouTube, Twitter, LinkedIn, the full works, or just search for Continuous Delivery and you'll find them straight away. Equally, if you wanted to get in touch with the Any Tech team, then there's our social media handles. As I said before, just go to any.technology and you'll find them all there. Any feedback or anything, or any questions or something, then do get in touch. Cool. So next month, it's funny you were saying about AWS and kind of their structure, because next month we have somebody from AWS coming to speak. So we've got Danilo Paccia, who's going to be talking about serverless architecture and kind of what we can expect in the future for that. So do make sure to sign up to that. So yeah, all that's left to say then is just massive thanks to Dave. Thank you everybody on the call for joining, because you guys make Any Tech, so it's always good to see people coming along. And yeah, hopefully we will see you next month. So thank you all. Enjoy your evening.